Hi, welcome to Algebra 2 Common Core. Tonight in Lesson 6, we're going to take a look at whether events are dependent or independent. And we're going to define those types of events and see how the dependence or independence of the events affects their probabilities. So let's start with the definitions of the two kinds of event. That's in the box at the top of your notes. Dependent events. That's defined as when the occurrence of one event changes the probability of another event happening. Independent event would be if the occurrence of one event has no effect whatsoever on the probability of another event. So let's take a look at the four examples in example number 1, and we want to classify them as either dependent or independent and think about why that might be true. So in A, I've got the two six-sided die are rolled. Well, when I roll the first one, I get 1 through 6. When I roll the second one, I still have exactly the same probability of getting 1 through 6. So that tells me that rolling two different six-sided die are independent of each other. Now that would also be true if I were rolling the same die twice, because what I roll on the first roll is not going to affect what I roll on the second roll. For B, 6 pieces of paper numbered 1 through 6 are in a bag. 2 pieces of paper are selected, one at a time, without replacement. So what's important in this problem is the fact that it is without replacement. So that means that when I draw a piece of paper from the bag the first time, there are 6 choices. But given the fact that I haven't replaced it, when I draw the second time, there's only 5 choices. So that's going to change the probability in the second draw. So that tells me that this scenario is going to describe a dependent event. Part C, a student taking a quiz randomly guesses the answers to 4 true and false questions. Well, for each question, they have exactly the same chance of choosing a true or a false. It doesn't matter what you've chosen on question number 2 for when you move on to question number 3. So if that's true, then guessing does not affect the next choice, and therefore these are independent events. And for the fourth one, it says your teacher chooses a student to lead a group, chooses another student to lead a second group, and chooses a third student to lead a third group. So no student can lead more than one group. So this is in effect doing exactly the same thing as no replacement. Once they choose that first student, that student is not in the running anymore for leader of the next group. So therefore, choosing students in a row are going to be dependent events because I have fewer choices to choose from after I choose the first few. Let's start by examining independent events and look at the probability. So in words, two events, A and B, are independent events if and only if the probability that both events occur is the product of the probabilities of each event. So you can see that when I have independent events in symbols, when I want the probability of event A and event B, then all I need to do is say take the probability of A and multiply by the probability of B. We actually looked at these types of scenarios in lesson number 2, but we didn't call them independent events. So let's look at an example of this. I'm rolling a die and I'm spinning a spinner that has 4 different colors. So I want to know what's the probability of rolling a number 4 on the 6-sided die and then spinning the color red on the spinner that has 4 different colors. So when you think about this example, it's clear that rolling the die and spinning the spinners have to be independent events because one does not affect the outcome of the other. So since they're independent, the probability of rolling a 4 on the die and getting a red on the spinner would be equal to the product of the probability of rolling a 4 on the die times the probability of spinning a red on the spinner. So the probability of rolling a 4, that's just one of the sides out of 6 sides, The probability of spinning the color red, since there are 4 sections on my spinner, that's going to be 1/4. So 1/6 times 1/4 is a 1 out of 24 chance of getting 4 on the die and red on the spinner. We could have, in our very first lesson in this unit, drawn a tree diagram for this and gotten exactly the same answer. But we want to get to the point where we don't have to rely on tree diagrams to calculate our probabilities. In example number 2, it says you play a game that involves drawing 2 numbers from a hat. There are 25 pieces of paper numbered from 1 through 25 in the hat. Each number is replaced after it is drawn. So again, that's an important piece of information that we are having replacement this time. Because I've got replacement, that tells me that my probability of the second draw will actually be equal to the probability in the first draw. I'm not changing how many I'm drawing out of. So since these are independent events, I'm even going to write that down, these are independent events, that means that I can do the product of the probabilities separately. So if I want the probability of a 3 first, and then a number greater than 10, that means I want to do the probability of 3 multiplied by the probability of getting a number greater than 10 because these events are independent. So the probability of drawing the number 3, there are 25 pieces of paper in the hat. Only one of them says the number 3, so I've got a 1 out of 25 chance of drawing the number 3. The probability of getting a number bigger than 10, count up how many numbers are bigger than 10. So that means 11, 12, 13, 14, 15, all the way up to 25. If you count those, there are 15 of them that are bigger than 10 out of the still 25 pieces of paper in the bag because I did replace the first one that I drew. So we can go ahead and multiply those together and we get for our answer 15 out of 625. And again, we could leave our answer like that, or I can reduce it by dividing the top and the bottom by 5, so I end up with 3 over 125. And again, I could change that to a percent or a decimal as well. Now, in part B, you'll notice that it looks like a very similar problem, but there's just something that's a little bit different. In the first example, we had a 3 on our first pick and a number greater than 10 on our second pick, so it was specified which one was which. In part B, it says you'll pick a 3 and then a number greater than 10. So in this case, we don't know which order the numbers or the cards will be picked. So therefore, we have to take into account both possibilities. We can either choose a 3 and then a 10, or we could choose a number, greater than 10, or we could choose a number greater than 10 and then the number 3. So I have to actually figure out both of these probabilities, and since it's an or that we're talking about with probabilities, that means that I can add those probabilities together. So if I pick the number 3 first, there's a 1 out of 25 chance of getting a 3. If I then pick a number greater than 10, that's the same as what we had previously, 15 out of 25. So when I calculate that, that's giving me 15 out of 625. Now, if instead I pick the number greater than 10 first, that's going to be 15 out of 25. Then I pick the number 3, so there's only one that says 3 out of 25 cards. So that's also going to be 15 out of 625. So when I add those pieces together, that's giving me an answer of 30 over 625. And again, that can be reduced. That would be reduced to 6 over 125. So you see that there is a slightly higher chance, in fact, there's a double the chance of getting a 3 and a number greater than 10 if it doesn't matter which order I do it in. So you've got to take that into account if order matters. In example number 3, we're talking about soccer players Madison and Kate. The probability that Madison will score a goal on her first attempt is 0.75, and the probability that Kate will score a goal on her first attempt is 0.82. For part A, it says let's calculate the probability that Madison and Kate will both score a goal on their first attempts. Now, Madison scoring a goal has no effect on whether Kate will score a goal. So that means that these, again, are independent events. So each time you look at a probability, you've got to say to yourself, is this dependent or independent? So with independent events, we are going to multiply their probabilities. So the probability that Madison will score on her first attempt is 0.75. The probability that Kate will score on her first attempt is 0.82. So when I multiply those probabilities together, that's giving me an answer of 0.615 for the probability that both will score on their first attempts. Now when I get to part B, it says Madison and Kate will both not score a goal on their first attempts. So I need to take a look at what the probability of not scoring a goal would be. So the probability of Madison not scoring, so I'm going to take the complement of Madison scoring, would be equal to 1 minus 0.75. Remember, whenever we have a complement, we have to subtract the probability of it happening from 1 to get the probability that it won't happen. So that's giving me a 0.25. The probability of Kate not scoring would be the complement of Kate scoring. So that's going to be 1 minus 0.82. So that gives me 0.18. So if I want the probability that they will both not score a goal, again, these are independent events because one not scoring a goal will not affect the other one not scoring a goal. So I just need to do the probability of Madison not scoring times the probability of Kate not scoring. So that's going to give me 0.25 times 0.18, and that probability is just going to give me a 0.045. So there's actually a very small probability that they won't score on their first attempts. So all of the examples that you have seen so far in this lesson have been independent events. So in each case, when I've got an independent event, that means that I can multiply the probabilities of the events together to get the probability of the independent events happening. Let's take a look at the next page where we're going to talk about dependent events. So when events are dependent, in words, two events, A and B, are dependent, then the probability of both events occurring is the product of the probability of the first event and the probability of the second event, given that the first event has occurred. So if I want the probability of A and B, when this time I've got dependent events, then I'm going to take the probability of the first one, A, and multiply it by the probability of B, given that I know A has already occurred. So let's look at an example of when this would occur. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. What is the probability that both students selected are girls? So once I choose the first student, that person cannot be chosen the second time around. So this is an example of without replacement. So if it is without replacement, that means that I've got dependent events. So with dependent events, let's take a look at how we are going to calculate the probabilities. So first of all, the probability of choosing the first student as a girl, there are 3 girls and we are choosing one of them out of 4. So there's a 3/4 chance of getting a girl on the first choice. But now, since she's already been chosen, she's no longer available for the second job. So now there are only 3 students left to choose from, and only 2 of them are girls. So we're going to multiply these 2 probabilities together, and we get 6 out of 12, which reduces to 1/2. In example number 4, we're talking about a bag containing candies. So with the bag that contains the candies, there are 2 red candies, 3 yellow, and 5 green. We call them sweets. Without looking, Mary takes 1 sweet out of the bag and she eats it. So clearly, because she is eating it, that means that we have no replacement. So with no replacement, our probability is going to change on the second draw. She then takes out a second sweet. So let's take a look at what probabilities we're trying to calculate here. In part A, it says if the first sweet is green, what is the probability that the second sweet is also green? So the probability that we're trying to solve for is this one right here. What's the probability that the second sweet is also green? So first of all, we're going to say if the first sweet is green, out of the candies, 5 of them are green out of 10 that are in the bag. Then we're going to say, okay, now if we've already chosen and eaten one of the greens, what's left over? There are 4 out of 9 left that are still green. So the probability that we're actually looking for here is this one right here. It's the probability that the second sweet is green. So this right here is my answer for this problem. In part B, it says if the first sweet is not red, what is the probability that the second sweet is red? So again, still no replacement because I'm eating the candies, and that means that my events are dependent. So for the first one, we're going to say we're choosing a not red sweet. So how many are not red? Well, 2 are red, so that tells me that 8, the 3 yellow and the 5 greens, are not red out of the 10 that were in the bag. But I've chosen one of those, so when I go to make my second choice, I want to know what's the probability of that one being red. Well, now there's only 9 left in the bag. I didn't choose a red on the first try, so there's still 2 left that are red. So that tells me that the probability that the second sweet is red, given the fact that the first one was not red, is 2/9. For our last example, we're talking about some botanists that are categorizing plants. So they have 60 plants, and these plants are going to be classified according to what type of leaf they have. Now it says that 15 of the plants had type A leaf. So I'm going to say A, there are 15 of them. 37 had type B leaf, and 8 had type C leaf. So altogether I've added those up and I can see my 60 plants. So I want to find the probability that when I select 2 plants at random, then both of the plants had type C leaves. Now once I select a plant, I'm not going to put it back in the garden. I'm just going to keep it, look at it, and categorize its leaves. So that tells me that this is again without replacement. Even though it doesn't come out and say that it's without replacement, we've got to take a look at the situation. So since it's without replacement, we're going to say that this is a dependent situation. Okay, so both plants had type C leaves. So when I look first of all at the first plant, there are, let's see here, 8 of them that have type C leaves out of the 60 plants altogether. But then when I want the second one to also have type C, I've already taken one of the ones that has type C, so I'm going to say there are only 7 of them left and only 59 plants in the garden. So when I multiply this, I get 56 out of 3540. This is not an easy one to do a reduction on. I can divide by 4, but I think I might change this over to a decimal. 0.016 rounded would be this probability. Now you'll notice that this probability was asking us to find the probability of both plants having type C leaves. So it's a little bit different than the last example that we had. Now let's take a look at part B. Neither of the plants have type B. So which ones do not have type B? Well, the ones that have type A or the ones that have type C. So if I want not type B, there are, let's see here, 15 and 8. There are 23 that do not have type B leaves out of the 60 that we have in our garden. We also want the second one to not have type B. So there's only 22 of the ones left that are not B out of 59 plants in the garden. When I multiply this, it's giving me 506 out of 3540. And again, if I convert that over to a decimal, that's going to be 0.14 as my probability. So today we've become acquainted with dependent and independent events, and we've used those events in order to be able to find a probability of more than one thing happening. We'll work some more with practicing these in class, and I wish you a very good night, and we'll see you again tomorrow. Bye-bye.